Good afternoon, everybody. My name is Omar Mohammed, and I'm here to present the paper titled Comparative Study Between Subspace Method and Prediction Error Method for Identification of Gas Turbine Power Plant on the 6th International Congress on Ultra Telecommunications and Control Systems, ICUMT 2014, Petersburg, Russia. We have the following main points to be covered in this presentation. We have the background to clarify our paper, and then we have the subspace identification method to discuss the mathematics and theory of subspace method, and then we will describe the process to be identified, which is a gas turbine power plant, and then we have the simulation results followed by the conclusion. As we said, this paper aims to develop a discrete time state space models for thermal power generation system using subspace identification method. The process chosen for this application is a gas turbine power plant. The method is then compared with the other identification method, which is prediction error method, with regards to computation burdens, complexity, and speed of solution production. Thermal power generation plants are very complex systems which embeds high uncertainty and many complex processes with multi-inputs and multi-outputs. On the other hand, successful implementation of control systems and online monitoring systems depends mainly on the simplicity of mathematical models and computation demands to solve them in a timely manner. The paper introduces an important applications of subspace-based methods of system identification with application to gas turbine power plants working in Libya. There are two main points, two main approaches for modeling, which are based on physical principles or system identification. Unfortunately, physical principle modeling is very complex procedure. We have spent maybe before in other research point, we have spent maybe 4 years in order to develop a physical principle model for supercritical process. But for this specific application, we preferred the system identification method because it is valued over physical principle modeling, because it gives mathematical equations directly identified from operating data of the real system. Thereby, it prevents the complexity that is associated, faced when modeling by physical laws, and needs more sophisticated assumptions and equations to give satisfied results. Consequently, we have the following main contributions of the paper. The paper presents state space model for gas turbine process, which can be used for prediction and control. It's well known that modeling the behavior of combusted natural gas to produce useful power by first principle could be challenging, because the thermodynamics and of the combustion process requires extracting the dynamic behavior of the necessary variables by partial differential equations and simplifying assumptions in order to convert them to ordinary ones. This paper, or the paper, resolves this issue by the method of subspace identification. Furthermore, a comparison is reported between the two famous methods of identification, prediction error method and subspace identification, for this specific application for developing state space models. It's not quite difficult to build models. The challenging and difficulties exists in how to make them reliable and good enough, and this can be made through this comparison. As a problem definition, we have to design this model from certain operating data regarding the input and output of the system. So we have to identify the constant parameter matrix A, B, C, and D, and also the sequence of states. So what are these? W and V are zero mean white noise innovations with covariance matrix as described below. The problem is then to identify or determine the system order and the system matrix A, B, C, and D. This is the basic algorithm for the subspace identification algorithm. In the literature, there are many algorithms which are used to identify many industrial processes in the literature. We have chosen among many other subspace identification algorithms, we have chosen this one, which is a numerical algorithm for subspace state space system identification N4SID, because we have this tool already built in the system identification toolbox of MATLAB. The general steps which are based on the advanced linear algebra are: first is to calculate the oblique projection from the future input and future output. This oblique projection and then used to calculate the singular value decomposition of the oblique matrix. The oblique matrix this is broken into three matrices. The matrix in the middle contains the non-zero singular values in the diagonal elements. The matrix on the left the first columns of the matrix on the left are the orthonormal basis of the range space of the main matrix, whereas the last columns of Q are the orthonormal basis of the null space of the main matrix. Then estimate the system order by counting the non-zero singular values of S and set apart this SVD to obtain U1 and S1. Then we calculate the extended observability matrix, which is used to determine the sequence of states. Up to this point, we have the sequence of states, the inputs and the outputs. So we can calculate through this equation. We can calculate easily. We can calculate the matrix A, B, C, and D from this equation by this square approach. For stochastic part, we can estimate Q, R, and S from the residuals as the expected value of these. The specific application for subspace identification, we have used the gas turbine system of Zweitina power plant working in Libya. Any gas turbine system has these 4 points. First, we have air compressor to compress the natural gas into the combustor gas or combustion chamber. Then at constant pressure, we have heat input. The heat is added as constant pressure in order to burn the natural gas before it is introduced to the turbine to convert in order to convert the thermal energy contained in the natural gas into mechanical energy in the turbine. The turbine is then used to deliver mechanical power to the electrical generator coupled to the turbine in order to get electricity converted from mechanical power in the generator. The exhausted gas is then rejected to the atmosphere or injected into a heat recovery steam generator in order to produce more useful power from the heat recovery steam generator. As model, we have 4 inputs and 2 outputs: compressor temperature, position natural gas, position pilot gas, and compressor pressure. And the output, we have the power in per unit and combusted gas exhausted temperature. There are always inputs which are beyond our knowledge and control. These are considered as noises and unmeasured disturbances. The problem has been handled using system identification toolbox developed by Iljang. The load dynamic data, which represents a load variations up to 75%, is imported to the tool for identification. However, as the prediction error method is also involved in the procedure of identification, it can be represented as another way of verification that's not described by subspace identification method. Simulations are conducted and the results are reported. We have here the power in per unit system. We can clearly see that the prediction error method is more accurate than N4SID for this specific application, and this is the corresponding exhausted temperature for the natural gas. We have from these outputs, we have the chance to design a controller, for example, as a future research, in order to control the real power delivered from the turbine, and also the exhausted temperature in order to control the efficiency of the heat recovery steam generator, which use the exhausted gas as heat input. We have the independence test and whiteness tests from the residual analysis, which represents another way of verification that is not described by the model, and we can see that the fluctuations of the autocorrelation residual for output Y1, the autocorrelation of residuals of output for output Y1 also fluctuating inside the confidence interval, which reflects that the model is well described the system is well described by the model. Also, the cross correlation between U1, U2, and Y1 residuals are here, and also the cross correlation of the input U1 and Y1 residuals. As a discussion for these results, we have observed that prediction error method produces the solution after 20 iterations, whereas subspace identification is not an iterative process. This can be considered as an advantage for subspace method over prediction error method. Prediction error method is more accurate than subspace identification, and this can be observed in the time-based dynamic responses of the system. That prediction error method follows the trends of the plant with less fluctuation around the real trends than subspace identification method, and this can be considered as advantage for prediction error method over subspace method. It is therefore not our target to decide which one is better. Alternatively, it can be reported that the two methods are a complement to each other. We have the following main 4 points as a conclusion. A model based on subspace identification has been developed in the paper. The method relies entirely on elementary linear algebra and matrix analysis, and the application is a very complex process, which is a gas turbine of power plants operating in Libya. Finally, we have the subspace method has shown promising results for the identification of real behavior of gas turbine power plants and compared with prediction error method. Many thanks for your attention.